Hello everybody, I am Alessandro Tundo, a PhD student from the University of Milano Bicocca. Today I'm going to present our research paper about self-adapted peer-to-peer monitoring system for fog environments. The work is co-authored by the master student Vera Colombo and professors Michele Ciavotta and Leonardo Mariani. Let's start by an introduction to fog computing, which has been proposed to fill the gap between the cloud and the Internet of Things, providing a continuum of computing, storage, and networking facilities designed to address emerging scenarios, such as, for instance, smart cities, smart transportation, Industry 4.0, or e-health. The infrastructure of fog computing is made of a large number of widely distributed heterogeneous nodes, which can include network devices such as routers, gateways, access points, and base stations, as well as microclouds and computing servers. As we get close to the things layer, the number of involved devices increases. On the contrary, the latency decreases, thus enabling real-time applications from the several domains we named before. Monitoring is a pivotal component for providers and operators because it provides reliable insights about infrastructure and service behavior. In particular, it plays a central role in fog environments where autonomous orchestration of services and platforms is crucial to end users' functionalities. Moreover, it is fundamental in the context of service-level agreements to solve disputes that can arise when SLAs are violated. Monitoring can also support the activation of operator-mediated or self-healing procedures in case of malfunctioning or failures. However, monitoring in the fog is non-trivial and poses several challenges to be addressed. The devices composing the infrastructure are heterogeneous and massively distributed. The topology is subject to frequent changes, with nodes joining and leaving the network unpredictably. And the predominant role of wireless access creates high variable network conditions, and the resources on some devices might be scarce, stressing monitoring solutions to make good use of available resources. Although a large number of monitoring solutions are already available for the cloud, they are well known to badly adapt to heterogeneous and massively distributed infrastructure characterized by frequent changes to the topology of the nodes, such as in the fog. Peer-to-peer architecture have been recently investigated as viable approaches to effectively address monitoring in the fog. They represent a legitimate option to address the dynamism without imposing strong constraints on the stability of the target environments. Unfortunately, although these monitoring systems show some degree of adaptivity, thanks to the feature provided by peer-to-peer architecture itself, they lack in adaptation mechanisms that take into account the monitoring indicators and available resources. In fact, the collected indicators reveal important information about the monitored system and its environment, and can be exploited to increase the awareness and adaptability of the monitoring system itself, for example, by enabling or disabling indicators when needed or changing the sampling rate. In this work, we use a two-tier hierarchical peer-to-peer monitoring architecture proposed by Forti et al., with followers at the lower layer and leaders at the higher tier. The benefit of employing such an architecture in the fog is twofold. First, it implies different roles for peers running in different tiers depending on the available resources. Followers are designed to collect data by running on the edge, within nodes and devices with limited resources. Leaders are designed to consume more resources to store the data received from the followers while creating and operating the peer-to-peer network. Followers are connected to a single leader and work in a classic client-server fashion. These distinct roles can be used to opportunistically exploit available resources, including the possibility to adapt to changing conditions such as bandwidth or resource degradation through dynamic peer promotion or demotion. Second, it helps reducing the network overhead by limiting the amount of data transferred between the peers. Actually, followers can forward data to their leader only, leaving the thinner upper tier with the possibility and the responsibility of building a global state of the monitoring resources by exchanging monitoring data among leads via gossiping protocol. In particular, the Fogman implementation is capable of collecting multiple indicators such as hardware resource consumption and network quality of service. However, adaptivity is limited to topology organization, and in fact, the set of collected indicators is static, as well as the sampling and transmission rate. These two aspects are fundamental to adapt to available resources and changing runtime conditions. To overcome these limitations, we propose a self-adapting monitoring solution, namely Adaptive Fogmon, that introduces the MapKey loop to peer-to-peer fog monitoring. The monitor component of MapKey loop collects data about the managed resource through sensors. In our case, this is achieved by monitoring probes running within the peers. The analyze and the plan steps analyze the collected data and plan for the countermeasures to be activated. Finally, the execute step exploits effectors to run the selected countermeasures. In our case, the countermeasures reconfigure the monitoring system according to the observation collected from the managed resource. The knowledge is shared among all the components. In other words, peers are capable of adapting the sampling and transmission rate and enabling or disabling the set of collected indicators by exploiting the knowledge about the indicator's trend. Note that MapKey loop runs within each peer, independently of the overall architecture, which gives peers the capability to run self-adapted behaviors regardless of their role within the architecture. We also evaluated the proposed approach in terms of accuracy, that is, we studied the impact of adaptive behaviors on the monitoring accuracy, and in terms of efficiency, that is, we studied the impact of the adaptive behaviors on the resources. In our approach, the knowledge consists of the monitoring indicators, which represent the raw knowledge about the monitoring resource, and the associated logical states, which capture the semantics of the values of an indicator. While time series of values simply reflect the sequence of probed samples, the corresponding time series of logical states captures the state of an indicator at a specific time, revealing information about the monitored resource. For instance, an indicator might be unstable, too high, or within a normal range of values. The states can be derived from the time series of raw values and used to find countermeasures. We defined a set of logical states usable for our countermeasures, but this set can be clearly extended depending on the countermeasures to be implemented. In the case of the domain of an indicator is categorical, we define two logical states, stable and unstable. A categorical indicator is stable at time t if its value has been constant in the recent history of the execution, otherwise it is unstable. In the case the domain of an indicator is numerical, we define 7 states: stable, unstable, normal, high, low, too high, and too low. A numerical indicator is stable at time t if its value is close to the previous one, and the indicator had small variations in the recent history of the execution. Similarly, a numerical indicator is unstable at time t if its value differs significantly from the previous one, and the indicator had significant variations in the recent history. The remaining 5 states detect values that still stay in a given region of the domain. Monitoring is rather natural and inexpensive in Adaptive Fogmon, since followers collect data from a monitored resource by construction, and thus the same data sent to the leaders is also available to the MapKey loop. If needed, extra indicators can be collected for the only purpose of controlling the adaptive behaviors of the peers, even if not needed by the applications accessing the data produced by the monitoring system. The monitoring behavior is controlled by a sampling parameter rate that determines how frequently values are collected and forwarded to leaders peer. The analysis mainly consists of a data processing routine that converts the raw values collected for every indicator into its logical state representation. In particular, the analysis process accesses the collected values and applies the definitions to the generated time series of logical states for every monitoring indicator. Our solution embeds the Eclipse expert system, which is responsible for determining the countermeasures that have to activate according to the accumulated knowledge based on a set of adaptation rules. An adaptation rule consists of 2 parts: an antecedent, that is a set of conditions on the logical states that must be satisfied to fire the rule, and a consequent, that is a countermeasure to execute. We extended Eclipse by implementing functions that can be used to evaluate the logical states of the indicators, such as functions that can check specific conditions on the last few samples of an indicator. These functions can be used as part of the adaptation rules specified using Eclipse domain-specific language. For instance, here we show an adaptation rule that fires the change rate countermeasure when the CPU consumption has a stable trend. The symbol arrow separates the antecedent and the consequent of the rule, and it's worth noting that the example adaptation rule uses some of the functions we defined. It first checks if the CPU consumption is in a stable state with the isIndicatorInState function, and it computes the new rate for such indicator by executing the computeIndicatorRate function. The new rate values is in turn used, along with other variables retrieved from the knowledge base, by the change rate function that implements the change rate countermeasure. During the plan phase, the expert system takes adaptation decisions, evaluating the antecedent of every rule and inserting the countermeasure, so the consequent, activated in a priority-based queue. Also, the activation of the rules is governed by the expert system that provides and prevents their simultaneous execution. To demonstrate the self-adaptive capabilities of the approach, we define two specific countermeasures, the select indicator and the change rate. The select indicator's countermeasure can change the set of monitored indicators, either activating or deactivating some of them. The change rate countermeasure changes the rate to sample and send data to the leaders based on the current trends of the indicators. The goal of the countermeasure is to gradually increase or decrease the rate while the monitoring indicator is less or more stable. During the execution phase, adaptive Fogmon merely executes the countermeasures by running their implementation according to their priority of activation. The actual countermeasure we define act on the configuration of the peers, adapting their behavior to the evolution of the indicators. We implemented our approach by extending the open source C++ Fogmon peer-to-peer monitoring tool along multiple dimensions. In particular, we extended the structure of the peer's local storage to store the logical states used to classify the monitored indicators. We embed the Eclipse rule expert system to support the implementation of the adaptation rules, and we extended the peers to incorporate adaptive behavior. We also added a helper function that can be used as part of the adaptation rules to interact with the knowledge, and we implemented the two countermeasures. The resulting prototype is publicly available with an open source license. I will now show the workflow of the control loop that implements the MapKey framework. First, the adaptive follower gets the indicator's value, for instance, value for indicator I at time t, and then it updates the monitoring data. The adaptive controller reads the time series from the data storage and computes the new time series of states at time t, and writes the states into the database. Then it triggers the rules engine that reads the time series again and sets facts in the knowledge of the expert system, and then checks the rules. If any, the countermeasures are then applied on the peers. To evaluate the approach, we compared our adaptive solution with the non-adaptive version, driven by two research questions. The first research question studies if adaptive Fogmon can improve the monitoring accuracy of Fogmon. The second research question studies if adaptive Fogmon can save node resources compared to Fogmon. We investigate the accuracy of the collected data considering synthetic indicators, following different representative trends. We defined 5 scenarios, mimicking different key cases, for an indicator conventionally ranging between 0 and 1. Here, stable is a time series representing a regular and stable behavior. It is generated by alternating two close values periodically. Unstable is a time series that represents an irregular and erratic indicator with fluctuating values in a range. We used a real-life trace on CPU utilization. Stable and unstable is a time series that alternates phases of stability with phases of instability. Random is a time series with chaotic and totally unpredictable values, and it is generated by a sequence of random values uniformly distributed in a range 0-1. Spiky is a time series with mostly regular values interleaved with rare spikes, and it is generated by alternating stable and unstable values and then a spike. Fogman and adapted Fogman followers pairs are configured to forward the average of the last 20 measurements to their respective levers at each probing point. The Fogman follower probe new values from the monitoring metric at a fixed interval, every 20 seconds. Adapted Fogman exploits the change rate countermeasure to adjust the sampling rate to handle the variability of the monitoring indicator. The hypothesis to test is that this can lead to improved monitoring accuracy because the leader should have access to a higher number of samples when the monitoring indicator is highly dynamic and fewer samples in the presence of more stable indicators. Every time series has a duration of 10 minutes except for the stable and unstable time series that lasts 20 minutes since it's a combination of the stable and unstable time series. We investigate the capability of the monitoring system to reconstruct the shape of the monitoring indicators at the level of both follower, which directly samples the indicator, and the leader, which collects a sequence of average values. We use the root mean square error, which measures the difference between the original and the reconstructed indicator, as the primary quality metric. A smarter sampling strategy should achieve a lesser error. To appreciate the activity of the pairs in relation to the monitoring indicator, we also gauge the message-second ratio, that is, the ratio of the messages sent by the follower to the leader. Finally, for the spiky time series, we also computed the percentage of detected spikes, which measures the capability of a monitoring technique to spot rare but significant events. We can observe that adapted Fogman estimates the observed indicator more accurately than the non-adapted version at both levels of the leader-follower hierarchy in 4 out of 5 scenarios. So the stable, unstable, stable, unstable, and random ones. The reduction of root mean square error reached 33.6% at follower level in the unstable scenario and 82.7% at leader level in the random scenario. A higher accuracy, however, comes at a cost of a higher number of messages exchanged in the 4 scenarios where the monitor indicator is more erratic, nearly 5 times more than Fogman in the worst case, and fewer messages produced when the indicator is stable, saving nearly 1/3 of the messages. These results demonstrate the capability of adapted Fogman to modulate resource consumption as needed, exchanging more messages only if the monitor indicator requires finer sampling, saving bandwidth otherwise. The spiky scenario is the only one resulting in an increment of the root mean square error for the adaptive follower. However, this increment is a consequence of the capability to partially follow the trend of the indicator. In fact, Fogman configuration could detect spike only incidentally, while adaptive Fogman could change its sampling rate to increase the chance to capture them. Although successfully capturing some spikes, the reconstructed time series generates a higher error compared to the flat time series reconstructed by Fogman. Indeed, this is a challenging scenario for both the approaches, and more work is required to design cost-effective monitoring techniques that can accurately address spikes. We can observe here an example of the time series reconstructed by adapted Fogman. The solid orange line is closer to the reference indicator, the dotted green line, than the Fogman version that is represented by the dashed blue line. It is also interesting to notice how the rapid change of the observed trend is not immediately handled by our solution, which shows some delay in sensing the drift and adjusting the sampling rate. In contrast, the non-adapted version always fails to follow the observed time series, confirming the importance of the adaptivity in similar contexts. Here we can observe the same behavior for the leader aggregated values. Research question 2 investigates resource consumption, considering the 2 countermeasures currently implemented, both in isolation and jointly. For these experiments, we defined a probe at the follower level only that exploits the Docker Engine API and PowerStop to collect some quality metrics, that are the CPU and memory consumption, the network input-output, that is a cumulative amount of data sent or received over the network interface from the beginning of the experiment, the number of processes or threads spawned by the peer, and the estimated instantaneous power consumption. The 3 adapted Fogman configurations assessed in this research question exploit the 2 strategies. Change rate adjusts the sampling and forwarding rates of the collected indicators from 30 to 60 seconds, based on the monitoring values. Select indicators disable the collection of all the indicators except of overconsumption if the battery's levels drop below a threshold. Combined, use both strategies. We study the impact of this configuration on resource consumption along with the Fogmon baseline. A total of 4 possible configurations are therefore considered. In each experiment, the follower peer is configured to collect the indicators from its node for 30 minutes and to apply the countermeasures at the beginning of the execution. In such a way, the impact of the countermeasures can be accurately measured. In fact, we collected more than 300 samples per each of the trick. We checked the significance of the differences between distributions with the non-parametric Mann-Whitney U test, as we observed via the Shapiro-Wilk test that such differences are not normally distributed. We specifically checked if the observed differences between the baseline and any other configuration are statistically significant, and also if the combined countermeasures is significantly better than the individual adaptation strategies. We consider the significance level alpha equal to 0.05, and we also compute the effect size of the observed phenomenon using the Wed's formula. The corresponding effect size uses the conventional categories that are small when it is less than 0.3, medium between 0.3 and 0.5, and large when it is greater than 0.5. We only observe marginal differences in CPU consumption. In particular, differences between adapted Fogmon and the baseline are not significant, and the combined countermeasure introduces significant but small differences compared to employing the other two adaptive strategies individually. The memory consumption results show statistical significance for all cases with a large effect size for all comparisons, except for the select indicators compared to combined countermeasures, where the effect size is small. While we notice an increase in memory consumption of about 10% for change rate compared to Fogmon, memory overrate decreases to about 3% when select indicators or combined are used. These results can be easily explained considering that although the map key control loop increases the amount of memory used by adaptive Fogmon when all probes are active, while when these are disabled, freeing the associated resources, the overall average memory usage decreases. We measured the number of subprocesses spawned by all compared configurations, and in this regard, the number of spawned subprocesses shows significant reduction with large effect size when select indicators and combined countermeasures are used, while it is small for change rate only. The results on power consumption show meaningful differences only for Fogmon versus combined countermeasures, suggesting that the individual countermeasures may introduce limited benefits. Still, the combination can significantly improve battery lifetime. The results for network I/O show statistical significant reduction for all adapted configuration compared to Fogmon, with an effect size ranging from small to medium for the input, as shown here, and from small to large for the output, as shown here in the next slides. Note that the results for input and output present a similar behavior for the same configuration. Results show a small effect size for change rate versus Fogmon comparison. Since we expected a stronger impact of rate adaptation in this context, we analyzed the behavior of the probes and discovered that the bandwidth gauge exploit IPERF, which measures the bandwidth by saturating it with packets. Such an invasive behavior nullifies the potential benefits of a dynamic sampling rate, and therefore, to further investigate this dimension, we repeated experiments by disabling the weight monitoring probe for both Fogmon and adaptive Fogmon. The impact of change rate is now remarkable, as shown in the right side of this slide, with the reduction of transmitted data ranging between 31 and 34%, with an higher reduction when both countermeasures are simultaneously active. In summary, we propose an approach for monitoring fork environment that exploits a hierarchical peer-to-peer architecture and is capable of adapting monitoring behaviors by amending the map key loop. We extended Fogmon's state-of-art monitoring tool and released the new prototype publicly. We also evaluated its monitoring accuracy and resource efficiency, finding that adapted Fogmon can help save network I/O and devices battery without impacting CPU utilization by paying for an extra memory consumption to store data necessary to run the adaptive mechanism. These results can be beneficial in the fog since monitoring systems are called to reduce network overhead without impacting on power consumption, especially when devices are battery powered. At the same time, even resources-constrained devices at the edge are usually well equipped in terms of memory, mitigating the impact of a limited extra memory consumed by the monitoring system. Future work will focus on extending the self-adapted capabilities by considering multiple application domains such as service-level agreements and function-as-a-service monitoring. We also plan to define logical states based on indicator semantic and to study how to exploit the map-key paradigm at the level of the whole peer-to-peer monitoring system to deliver adaptive capabilities at system level instead of individual peers only. Finally, we would like to explore machine learning-based approach for the analysis and plan phases of the map-key framework. And that's all, folks. Thank you for your attention.